So far what we have covered is all about the biorefinery aspect, how to establish a biorefinery, and that is what you have your assignment as. If you remember, establishing a biorefinery for seafood, you had what is the biomass, what is the composition, what are the end product you obtain, what are the side stream you obtain, and from side stream what is it rich in, and based on that you come up with the product. So that one I'll just have a quick recap later on when we go through the technology. You can have a look at it. Yeah. So that's one, and we did discuss about the plasma, and previously we used certain examples of high pressure processing, mainly for stabilization of biomass as well as improving the shelf life of the product. Yeah. Now we'll go through, for example, with the cavitation technologies, that is cavitation based on formation of cavities. These cavities can be formed because of water, that is hydrodynamic cavitation, or because of ultrasonics. So they do have both processing application as well as extraction application. So this is again the specific part of your novel technologies application. One itself is related to germination and drying. Yeah. If we use what we need for germination of anything, for any grain germination we need only moisture. We don't need a soil, we don't need a fertilizer. So if you have a technique which can absorb the water faster, so it will germinate faster. Yeah. So ultrasonics having one such application. Second one is drying. So even sonics treatment can leave the micropores on the surface, which also can improve for drying, as well as you have seen some example of airborne acoustic, how that can also be used for drying purposes. They are just representative examples. So we have post harvesting operations, food preservation, microbial inactivation either by sonication or thermosonication, and leading to improvement in shelf life of liquid, semi-solid and solid food products. So that is again food preservation. Nutritional aspect. So when we use cavitation, we have a capacity to preserve the nutrients because it does not cause much of degradation of nutrients. Extraction technologies, it's used extensively. Now it comes here for allergens. So whatever allergens are, it is also useful in modifying the functionality of the protein, that altering the properties of protein. Hence it can also reduce the allergenicity or increase the allergenicity. Yeah. So ultrasound is not always for inactivation but also for activation of microorganisms. Peptide production, same way, enzyme plus ultrasound or ultrasound followed by enzyme. So that is all for peptides. So this is all related to nutritional aspect, related to processing as well as extraction side. Functionality, ultrasound assisted crystallization of fats and sugars. Ultrasound is one of the technique which can control the crystal size and type of crystals. Mixing and homogenization, that means ultrasonic, if you have ultrasound equipment or access to it, take water and add oil to it and give ultrasound treatment, you will see perfect emulsion formed. That is again for mixing and homogenization. So other one is valorization. So extraction of high value ingredient, wastewater treatment, that means again breaking down of dissolved solids and improving reduction in BOD and COD. So if we use cavitation along with ozone or with the plasma, we also can achieve advanced oxidation processes, that is cavitation will help in diffusion of those ionic species into the matrix and enhances the distribution. So this can be used not only for processing but also for preservation and valorization. So all these applications can be for cavitation, and there are number of different review papers and literature is full of different applications of ultrasonics. Yeah. And there are already 2 dedicated journals itself on ultrasound. One is ultrasound sonochemistry, other one is ultrasonics. Yeah. So you can see the amount of application and science related to sonics. So that's if you look at the different application, as far as I am aware, there are more than 50 to 60 or close to 100 applications are there, but 50 are almost used in different scales for different application across agri-food sector. Yeah. Some examples will quote it what are related to biorefinery aspect. Now when it comes to ultrasonics, what are the key parameters related to that? This is very important to understand. I don't want it to, how many have seen ultrasound working and noise of ultrasound? You can see this one. So, first and foremost important one is ultrasonic frequency. Yeah. So, sound operates based on frequency. What I am talking is also based on frequency. It moves based on compression and rarefaction. Liquid sound is different, metal sound is different, vacuum is different. Second one related to processing is your amplitude. It is the amplitude which is the guiding force for ultrasound. Ultrasound power, ultrasound intensity and ultrasonic power density. So, all those things, if you will see, this is ultrasonic probe, yeah, and this is normal water. How we play it. If you will see, if you add a small amount of powder to it, and the moment you give a blast, just observe the video, yeah, and that is ultrasonic probe which emits the cavitating bubble. And what you will observe is all these bubbles, these are all cavitating bubbles, yeah. So, if you are using a spoon or anything agitated, it will take ages to mix it together, yeah. So, this is a clear-cut example of just the mixing. But here again, if you have a water and oil, it will create milky color texture, milky color liquid that becomes exactly as an emulsion, yeah. So, all of you know about electromagnetic spectrum. Light, this, infrared, microwave, audible, and then different megahertz region. So, where all ultrasonic is used? Ultrasonic is used for both diagnostic purposes as well as processing application, depending upon the frequency. So, ultrasonic equipment, whatever is sold in the market and whatever is available, they operate only on a specific frequency. What you can change is only the amplitude, ultrasound power and ultrasonic intensity, yeah. So, amplitude is distance between two nodes or antinodes, yeah. That is again you have seen the classical Bell experiment, you hit it and then it start moving. So, if one is operating on a specific frequency and if you bring the another one of exactly the same frequency and they will go in sync, yeah. That is the way all the communication and everything is carried out, yeah. Now, this particular transducer is made up of piezoelectric transducer, yeah. How many of you know about piezoelectricity? We did discuss about piezoelectricity as a quartz, yeah. Can you give the mic to me? Yeah? One second. Yeah, go on.
Compressing or stressing a piezoelectric material, we get there is a change in the electric field of the resistance of the material.
Correct. So, if you press a material, their positive negative current separates and then you can get electric current. The simplest one which is used extensively is the quartz. Every watch is having a quartz in it, yeah. That is a piezoelectric property. So, when you apply a pressure, you can generate electric current. Same way, when you generate electric current, you can when you put electric current, it generates the pressure. So, that is piezoelectric transducer. If you see ultrasound, it says piezoelectric transducer. That is property what is used in these type of transducers. Similar properties are also there in biological materials. So, if you have any of the plants, if you will see, they also contain piezoelectric properties. Simple experiment is when pea plant grows, if you put one bamboo stick, one green plant and one metal rod, and you will see the node of that particular pea will go to a specific direction, yeah, how it senses. And these biomass, even chitosan also contains piezoelectric properties. Any material which can have separation of with application of pressure, it separates the current so that you can generate the electric current, and that can be used for making future batteries or different pressure system. Yeah, one of the latest example of piezoelectric properties for making pacemaker batteries. Lot of patients, they have pacemaker is installed and needs a battery. So that particular battery is replaced with a piezoelectric material, so that heartbeat, which gives the pressure, which will activate, which will keep that particular pacemaker in business by providing sufficient electricity. So these are the some of those advancements happening even in lot of institution in India. There are lot of experiments and protocols are ongoing how we can take electricity from a growing plant. When plant grows, there is also ability to get electrical current out of it. Yeah. So the purpose is plus and minus current like that. So this is again difference between two crust is your amplitude. So when it comes to equipment, how many of you have seen ultrasonic equipment? You have seen it, yeah? So have you seen a bath system or like a bath?
Sir, without bath system.
You've seen the probe system?
Yeah.
Okay, this type, yeah?
Yeah.
Okay. Now can you give it to her, yeah?
Bath system, sir.
Bath system, yeah? So what is the difference between a probe system and a bath system? We'll go through that one, and if you have any question, feel free to ask. So getting the clarity is very, very important, yeah? So what we can change is basically amplitude, power, intensity and acoustic power density, yeah? So unit of amplitude is going to be in unit of distance, that is micrometer. Amplitude cannot be anything. Power, watt, yeah? Ultrasonic intensity, watt per centimeter square. That is dependent upon the radiating surface. If probe is of 1 centimeter diameter, area of the probe will be 3.14 centimeter square, yeah, because pi r square, I am wrong. 1 centimeter, that means 1 upon 2, that means 0.5 centimeter, yeah, that is pi r square. What I am saying is if radius is 1 centimeter, yeah, radius is 1 centimeter, area of the radiating probe is pi r square, that is 3.14 centimeter square, right. So if that radiating surface and watt is measured, watt upon the radiating surface becomes ultrasonic intensity, yeah. And acoustic energy density is if you are treating 100 ml of water, so what you know, watt per ml will become acoustic energy density or acoustic power density. So this was the unit was first established by ourselves. We did that with the what way we calculate ultrasonic intensity. There are multiple other ways of calculating ultrasonic intensity. Having ultrasonic bath, you put your aluminum foil, you have seen those experiments. Amount of aluminum which is removed from that foil, that could be one way. Second one is the measurement of hydrogen peroxide. When we do sonication, it breaks the water into OH and H plus, and that gives you idea of how much hydrogen peroxide is formed. But all are dependent upon power, because ultrasonic power is the easiest way to estimate by using caloric method. Sorry. So that is all the basic about ultrasonic. I will come back to you how do we measure ultrasonic power. Now another thing related to this ultrasonic system is, if you did your experiment for 100 ml water and then now you want to use the same condition for 200 ml, it won't work, yeah, because acoustic energy density distribution is changed, yeah. That is one of the limiting factor when it comes to scale up. So when you have to scale up, you have to accordingly balance out acoustic energy or power density going in. What I mean is, if you are putting 10 watts for 5 minutes in 100 ml, so if you increase 100 ml to 1 liter, same amount of power should be gone to 1 liter. So you have to increase the time, yeah. So that's the way scale up operations are carried out. That is applicable to every technology, whether it's plasma or plasma, pulse electric field, any technology, whatever you deal with, you have to work accordingly. So how we can calculate ultrasonic power? What is given on the machine is the machine rating, yeah. This television or this projector is working on 2000 watt is a maximum it can draw out the power. or a fan with the 600 watt is the maximum power, but if you are using at lower speed, you are only taking 50 watt, 100 watt or 200 watt. Yeah? So, that is nothing to do with ultrasonic equipment power. So, those values which are written on the publication and things, they are not correct precisely. That is one of the reason you cannot reproduce some of the work which is already there and based on the similar conditions. Yeah? So, if you do something with ultrasonic bath and you do something with the probe, both cannot be replicated. Reason is simple. In ultrasonic bath, anyway, I will show it to you in next slide. Yeah. So, this is again electromagnetic spectrum. Yeah. Before going into the application, I will say how we calculate a power. Suppose this is your beaker, yeah, and you have a probe in it. You put 100 ml of water. Yeah. 100 ml of water, what will be the specific heat of water? 4.18 kilojoules per degree Celsius per kg, correct? Specific heat of water, amount of heat required, that is joules, to heat a water or per kg of water by 1 degree Celsius, right, that is 14.5 to 15.5. So, this is a specific heat. So, when you start when you start the ultrasonic system, temperature automatically increases. Yeah. When temperature increases, if you measure the temperature, that is rate of change of temperature over time, that gives you dT by dt. Yeah. That means, if temperature increases over time, yeah, so you measure the slope of that particular line. Slope of this one will be, suppose this is your temperature and this is your time. Yeah. When you take a slope of this, so dt means delta t. Yeah. And those who are from physics or maths background, they do understand that. And this is time, right? You measure the slope of this. So, calculation of power will become, what is the equation of power? M Cp delta T by delta T. Yeah? Slope, you get it from here, specific heat is here, mass is 100. Yeah? So, you get your power. This is calorimetric method for measuring the power of ultrasonic system. Now, the question comes in the moment if I add a juice to it, yeah, or a food matrix. We only power represent through distilled water, because specific heat is remain relatively the same. Yeah, and you all know the specific heat changes with the temperature, with the pressure, with the compounded material. Specific heat of orange juice plus pineapple juice, it will be difficult to determine. Yeah. So, we just get a representative of getting calorimetric method. Yeah. So, then this way you get your watt, then you know about the diameter of your probe, makes an ultrasonic intensity. Whereas, when it comes to bath system, the radiating surface is bigger. So, power will not be the same what you get it from 200 watt probe system versus 200 watt bath system, because ultrasonic probe is attached to a flat surface and whole surface is radiating. So, intensity is reduced. Yeah? That is why comparisons are not easy to make between a bath versus probe. You might come across lot of publication or lot of papers, it says ultrasonic probe is better than ultrasonic bath. It is correct, but it is not level playing field, because one is not able to deliver the power what other is able to deliver. Yeah? You carry out the race for 200 meters, you ask Usman Bolt to run and you ask a 5-year-old kid to run. Yeah? Both are humans. Yeah? You can't compare it. So, the similar way. Now, when you look at the frequency sweep, infrasonic, acoustics, human hearing zone is over here. Yeah? And ultrasonic, anything above 20 kilohertz is classified as ultrasonics. So, majority of the processing application are between 20 to 100 kilohertz. Some applications are there at this zone, but anything above 5 is goes as a diagnostic one. So, this will be called as high frequency low power ultrasound. This is low frequency high power. So, majority of these applications are related to Majority of these applications are related to making sensors, diagnostic purpose, detection of tumors. How many of you have gone through ultrasonic in hospital? You put a sensor, it tickles, it sends sound waves and it determines the structure. Yeah. So, all these one lower frequency, cleaning, cavitation, higher power. Yeah. Low power, imaging, sensors, microscopy. So, this is the way ultrasonic system can work. Now, when ultrasound operates, you get both mechanical effect and a physical effect, both are same anyway, mechanical and chemical effects. Mechanical effect can be used for crystallization, degassing. In almost every chemistry lab you will see ultrasound, and people who are working on analytical chemistry, they use ultrasound for removing gas, degassing, because cavitating bubble gases are removed. Yeah. So, that is degassing or foam destruction. You will see one or two examples here. Extraction we already discussed, mixing, homogenization, brining and tenderization, freezing, encapsulation, drying, tempering. Just now I gave you an example where you have oil and a water. If you give ultrasonic treatment or even a blast, it will give you a perfect emulsion. Yeah. Same way, if you have a starch solution, you give an ultrasonic treatment, it will form an emulsion. So, that means this is one way of doing encapsulation. Encapsulation is covering of any ingredient with filler material, that is bioactive, covered with other, what do you call the outer layer of encapsulation? Protein or starch or any of those material can be used for encapsulation. Now, if you do it at a microscopic level, micro encapsulation. Yeah. Capsules what we consume as a medicine, they are also in capsules, they are also encapsulated outer covering. Yeah. So, it is not to bug down with the terminology. Other one is a chemical or a biochemical effect. Bactericidal action because of production of free radicals, effluent treatment, that is again reduction of BOD and COD, modification of living cells. Previously I said you can use ultrasonic to activate the microorganism as well as inactivate the microorganism depending upon the condition we use. Yeah. Very similar to a temperature. If you use 70 plus temperature, you will kill a microorganism. Whereas, if you use 30, 35, 40 degree temperature, you increase the microbial growth. Yeah. Similar principle applies here also. Alteration of enzyme activity, because you can modify the protein properties, hence you can modify enzyme activities. Sterilization, like thermosonication, heat plus ultrasound will cause sterilization effect. Yeah. So, this is all how ultrasonic can be used. I have not listed other application like soil treatment, soil remediation, heavy metals, coating. Ultrasonic is used extensively for non-food applications also. Yeah. Now, if you look at the processing equipment, we already discussed just now about bath type and probe or horn type. Yeah. That will need a medium to deliver ultrasound. Yeah. What way we are communicating, though it is not ultrasound, but it is air which is we are using it as a medium. Yeah. That goes as airborne acoustics. Now, if you see, this is the bath arrangement where the transducer is placed at the bottom. Yeah. Or transducer are based at sides depending upon the system. Even two bath system you cannot compare, because that depends upon how the transducer is configured. Yeah. Probe system, very same transducer is injected directly into liquid. Yeah. And this is also a transducer. This is a flat transducer, you can add it into any bath system. This is not a probe, but a transducer which operates at 400 or 600 kilohertz. And this frequency is very good when we extract oil from olive oil, pomace or any of those biomasses. Yeah. And there is no relationship between frequency and extraction. What works at 25 may not work at 45 or may not work at 100. What works at 100 may not work at 600. So, it is always its ultrasonic is case dependent. Yeah. So, that is why the huge amount of applications keeps coming in for ultrasound. Even solid mercury or liquid mercury was prepared by institute in Israel by using ultrasonic. Yeah, nanocarbons, carbon nanotubes activated, carbon nanotubes were prepared using ultrasonic. The black color powder which is formed, there is a lot of different application. Now this is also ultrasonic bath, but at larger capacity. Yeah. Now these are different types of probe system. How many type of probe system you have seen? You have seen single probe, yeah? So, sorry.
Sir, I have seen single probe, but different size, different length.
So, different size and length, that means they deliver different amplitude level. In order to know the amplitude level, you have to go to the manufacturers. They only can tell you what is the amplitude of that machine. Measurement can be done, but again you need a precise tools to do the micrometer measurement, right. So, that means different diameter, that dictates how intense you are delivering the ultrasonics to it. Yeah, that is important here. Now, when it comes to ultrasonic, as time progresses, you will see the holes in the probe at the bottom of it. Yeah, that is called pitting after certain size. That is what is written here. Repeated usage of ultrasound will, initially when you buy it, it is perfectly smooth. As you operate, it starts removing the titanium. Most of the probes are made up of titanium. So, that removes the cause pittings on the surface. Easier way to remove it is to grind it to make it smooth. Yeah? And other one is you get a replacement tip. You just replace a tip, you attach to it. Yeah? Similar way, boosters are attached to ultrasonic probes. Now, if you remove it and similar frequency, tuned frequency, you can get it for clinical application. If suppose you want to study impact of ultrasound on 96 well plate, you can have 96 probes, so that you can measure a probe to prove the concept. Then this is your probe system, and this is batch up to 1 liter or so. And this is a very similar process where you have a vessel where you have liquid coming in. Yeah. This is for controlling the temperature, liquid goes in and product comes out. Yeah. So, how we scale this one? Suppose you need only 5 minutes treatment time for 100 for 1 liter, and this vessel is of 1 liter. You control the flow rate so that whatever liquid passes through this gets 5 minutes treatment. That is the easiest way to scale up, or a simplest way. Or else you need to know the acoustic energy density, and based on that we can scale it up. Yeah. Now, if you will see here, suitability limited to liquid or food immersed in liquid medium, because you need to have a liquid there. And one question comes all the time is, if we are using ultrasonic all the time, the pitting, that means leaching of material, comes into the liquid food. Yeah. We carried out that experiment extensively and spoiled almost 10 to 15 different types of probe to see amount of metal which leaches. So, the amount of metal which leaches is exactly the same way we keep using the pressure cooker, and you see slowly the metal, whatever vessel you are using for cooking, it removes the metal. Yeah. Similar thing happens here, and after the prolonged application also, the residues in the samples are much lower than the standard of that particular water. Now, if you have read about ultrasonic, everywhere you will see the temperature of 3000 Kelvin or pressure of 400 or this much. 3000 Kelvin temperature is of sun's surface. Yeah. So, you are using an ultrasonic, so how you can create such a high temperature? What is the basis of that high pressure and that high temperature? The basis of that high pressure and temperature is indirect measurement, because if you need that much amount of temperature to break the water, based on that, when it breaks the bond between H2O, H2O is not is not an easy molecule to break into H plus and OH. It needs huge amount of energy in terms of temperature. Yeah. So, based on that temperature, these type of energy is calculated. Yeah. That is why you will see like 3000 Kelvin or how many megapascals, couple of thousands of pressures are reported, and these are all measured and established how much it can generate. Yeah. If you see your own classical textbook of flame, what is outside temperature, what is inside temperature. Light blue is the complete burning of fuel, temperature map of any candle when you burn. Yeah. Yeah, any question? Yeah. Okay. Now this comes airborne acoustic. Yeah. This is ultrasonic plate which delivers ultrasonic at higher frequency, 25, 50 or 55 depending upon how it has been fabricated, and it delivers the cavitation in this particular manner. Yeah. So as you can see, the gap is 40 centimeter, and one or two examples you have seen in with the plasma on airborne acoustic treatment. So this is the transducer, piezoelectric ceramics to transfer the electric current into the pressure transducer, and it gives ultrasonic waves through this. Yeah. This is airborne acoustic, completely non-contact. Even these systems can be used as a non-contact if you have it in your beaker, or if you are having it in your pouches or in surfaces. Now when we use ultrasonic system, lot of places you would have seen people, they use round bottom flask. Yeah. That is completely wrong, because ultrasound will deflect. It always have to have a flat bottom. Yeah. If you are putting in a bath system, it's a round bottom, so how much surface is exposed to it. Yeah. So there are some fundamentals of using ultrasonics in chemistry. There are certain books are there that is very important to read before you start using ultrasonic for any experiment. This is one system configuration based only on ultrasonics. A. Second, now you will be happy, ultrasound plus heat. You are working on thermosonication, right? So what you are doing?
Sir, giving moderate temperature with ultrasound.
Moderate
40,
temperature.
Yeah, is 40 kilohertz of frequency, and the temperature is about 50 to 60.
Okay. So when you use heat along with ultrasound, it becomes thermosonication. If you use ultrasound plus pressure in a pressurized chamber, it becomes manosonication. That is combination of pressure and sonication. If you use all three together, it becomes manothermosonication. Very simple. Yeah. Based on combination, these nomenclatures are in existence. So if you use 72 degrees Celsius with ultrasound, you can kill the spores. Yeah. That becomes, ultrasound helps in causing the pores on the spores, and when the temperature is used, it helps in killing that particular spore. Now it becomes slightly complicated. Now we go with this. Yeah. Now if you see this particular system, sometimes we may have to use multiple frequency system. Over here, this is 45 kilohertz bath system, and these are two probes both of 20 kilohertz, that is dual frequency system. Yeah. And this is a commercial level pilot scale system was developed, and you will see the application of this. This is your tank to supply cold water, cold brine to this particular vessel, and having ultrasonic bath as well as probe system. Second combination, as you can see, this is a domestic microwave, yeah, which was modified to do the treatment. Now looking at this, you do not have to modify the microwave. This is not that easy to do it. A trained engineer has to do that, where to cut that particular microwave. And as you can see, ultrasonic probe is going into that particular microwave. But this ultrasonic probe is not made up of metal. This is custom built probe, which can be also classified as a plastic probe, yeah, which is dipped into microwave to get the combination of both probe system and microwave together. So we had our own IP on this, which was lost because there was a French system which designed much better system, having ultrasonic at the bottom and microwave coming both into the steel vessels. How many of you have added the spoon into a microwave? What will happen? It will cause spark, yeah, because in microwave we can put liquid or solid food, but the moment metal goes in, it starts causing spark. But in this case, microwave goes into the steel vessel and ultrasound is at the bottom. The trick here is ultrasonic moves with a specific frequency. That is why, how many of you seen microwave, domestic microwave? Yeah? There is a rotating plate. Yeah? If plate is not rotating, there will be burning at a specific points. Yeah? This just because microwave also travels in a in a wave. Yeah? It is electromagnetic wave. So, if it is moving, so that it is having uniform heating. So, in this case there is a Teflon stirrer which moves, which guides the microwave, does not allow metal to come in contact with that particular microwave. Yeah? And when we use metal and ionic current into microwave, we can also generate microwave plasma. Yeah? Now, this is this is all to do with, oh sorry, this is permanent one. Yeah. So, this is basically, if you look at ultrasound and supercritical, this is supercritical system which would, I was trying to remove this circle. So, this one is having a vessel, this is a controller where the CO2 is pressurized, passed through the bottom of this tank, sample is loaded inside and then liquid CO2 goes out, pressure is released and you get your product out. Yeah. Now, the design was done when the CO2 is in liquid state to use ultrasonic to disrupt the matrix. Yeah. You won't have seen much in the literature and you won't be seeing it because we only got it designed recently and that is still looking at it. The purpose here was something like you have a hexane, you add into the matrix, so oxalate 6 hours to get the lipid, right. But if you disrupt the matrix along with the hexane, recovery can be done in a shorter time. Same thing when you are using a supercritical CO2, it will take longer to extract all the oil from the biomass. But if you disrupt the biomass along with the liquid CO2, so it will have a better extractability. So, for that reason ultrasonic system was attached along with this. Yeah. So, this will be synergistic aspect of both supercritical as well as ultrasonics to be exploited. Yeah. All these combinations are not done just because like a Lego, the kids they play Lego, they made a truck out of it, they made a tractor out of it. It is not added just like that, they are added for a specific reason. I will show you some of the examples in coming slide. Now, we discuss about the plasma jet or steam. When you throw a plasma, it moves in a form of air. Yeah. So, in order to direct that onto the surface, if suppose this is a full of plasma species, if you remember I was saying if you have to inactivate the biofilm, that species should enter into that particular matrix to kill it. Yeah. So, there airborne acoustic helps in suppressing those reactive species into the matrix by causing the pores on the surface. Yeah. So, majority of the combinations are based on the logic and what works, what does not work. Steam treatment, if you do the steam washing, you would have seen the steam jet washing, they are pointed. But if your steam jet is in a flat layer and then you suppress the steam, then you will have a uniform cleaning just to improve performance. Yeah. So, it will have lot of different voices, and when we talk about cavitating bubble, look at this. This is a cavitating bubble and how it implodes, and this is what is known as microjet and explosion. Yeah. Because of that you get all those reactions. When you read ultrasonic, says formation of microjet, acoustic streaming and all those things. Yeah. This is all to do with cavitating bubbles. Yeah. So, this is the bubble, look at it again, vacuum, and this is imploding, and because this implosion it is forming microjet. Yeah. Now, here this is microjet formation and these are now if you will see here, I am not going to turn on the sound, 10 micrometer, these are cavitating bubbles. Yeah. These are at different now. If you want to measure these cavitating bubbles, yeah, diameter of these bubbles can be measured and can see the reactions. How can you measure that? What do you need? Very high speed camera. Yeah. If you have high speed camera, you can track the bubbles to see how the cavitating bubbles operate. And this is the same 20 kilohertz ultrasonic system. Yeah. 20 kilohertz frequency system operated at using 125 micrometer probe. This is your different percentages of amplitude, and accordingly there will be power. So as you can see, this is all acoustic streaming, microjet, and single principle is cavitating bubble. Yeah, cavitation is single principle, rest all are effects of it. Yeah, and it makes really very loud noise. Yeah, and when you are using ultrasonic, is suppose 750 watt, and if you want to really use 750 watt, take that ultrasonic probe, put it into wood. Yeah, any hard surface like wood or anything. So ultrasound will always try to vibrate at the same amplitude. If it doesn't get that much of place to vibrate, it will use the full power, and if it's not able to use full power, it will gone. Yeah, that is overloaded. So for that reason, boosters are used. So if you put a water, it will make loud noise. Put 2% sodium alginate solution, voice will be completely low. It's just because this sound is not because of ultrasound, but because of those cavitating bubbles which are forming. Yeah. So that's why ultrasound does not make any sound, because if it makes sound, we can hear it. Yeah. If you turn on ultrasonic bath without water, I know, never, don't try it because it will spoil the system. It won't make any noise. The moment you put a water, it gives the sound. That is all because of bubbles colliding with different matrices. Now, if you look at this particular system, anything when you have direct field pressure, this is simple compression and rarefaction. Yeah. So nothing happens. Second way is stable cavitation. That is, cavitating bubbles are formed. Yeah, and they are just vibrating. Yeah, that is stable cavitation pressure. Transient cavitation, when bubble is formed and it is vibrating, exploding, imploding. So there are two types of cavitation: there is stable cavitation and transient cavitation. That means in this case, sound wave is going, particle is happily standing there, just simple. In these cases, micro streaming happens. That means bubbles are formed and they are moving here and there. Yeah, like what you saw it in the video, all these bubbles whichever are moving, that is micro streaming. Because of that, it dislodges the particles or disrupts the matrices. Another aspect, advanced one, goes in to make shock waves. Somebody is working on a shock waves. That is one of the way also to produce electric shock waves or sound shock waves. Yeah, and jet, formation of jet, and this causes disruption of matrices. Yeah, so the single principle is cavitation. This cavitation could be stable cavitation, transient cavitation, and these cavitating pressures can be calculated and can be estimated by using a specific type of sensors. Yeah, as you can see from here itself, all these cavitating bubbles when they are moving and how they are forming jetting system. And this was done with the normal camera in a beaker, clear beaker, to get those videos. Yeah, and the purpose was to measure those bubbles. Then we realized we need very high speed camera, which is quite expensive, to slow it down and then to measure the bubble and what is the fate of that particular bubble. Yeah. Now this is what I already discussed briefly, right? Now power, MCP dt by dt, the same delta T. This is differential, because when you are measuring temperature over time with different amplitudes, you get the slope of it. Yeah. Once you get the slope of it, you get this value. Yeah. Specific heat you know, mass you know, you get power in terms of watt. Yeah. Ultrasonic intensity, power upon surface area of radiating surface. Yeah, that is pi r square To make it more fancier, you do pi d square by 4, because diameter is easy to measure, whereas radius is difficult. Yeah. Acoustic energy density, power upon volume. Yeah. I will ask you a question. Suppose there is a tree trunk. How can you determine the radius of a tree? By using a vernier caliper. Yeah. How can you measure a diameter of a tree? By putting a scale or something. What is the easiest way of doing it?
Sir, we will measure a small area and then we will integrate the whole.
Mathematician, good. Any other simple technique? How I can measure? I have studied only agriculture. This was the question which was asked by my own undergrad UG teacher when we had a module on agriculture engineering. Yeah. There was a simple way. There you use a basic math, take a thread, tie it around 4, you measure the parameter, that way you can calculate a radius. Yeah. Make sense? Because the question was measure the diameter of a sugar cane. Oh, I need a vernier caliper. That's one. For measuring the distance from this wall to this wall, you need a measuring tape, but a technique called pacing. Yeah. So you know what is the distance between your normal walking. Or if your shoe is around 10 number, 9 inches or 31 centimeter, 30 centimeter, shoe after the shoe, you can get rough estimation, right? So everywhere you will not have those sophisticated tools to measure it. Yeah. So always try to see some first one is a simple solution, then to go for complicated one. Yeah. That's correct. You can use mathematically and all. Yeah. But how do we measure it? How do we know whether it's 12 o'clock or 6 o'clock based on ratio? If you see the old historical way of measuring the time. Yeah. So all those techniques are very useful in a practical application. Yeah. That does not mean we should not know the advanced method, but basic method knowledge is equally important. Yeah. So that was a simple one. Just take a thread, measure it around. You know the parameter. Parameter formula is pi d. Yeah. 2 pi r. That is pi d is parameter. So pi d is equal to the length of the wire or thread, and then you get your diameter. You don't have to have a vernier caliper. You don't have to cut anything to do all those integration and disintegration. So other complicated. This is simple method of measuring it. Other ones, acoustic emission, acoustic pressure distribution, cavitational efficiency, bubble collapse intensity, bubble temperature, number of cavitating bubbles. These are other ways of measuring energy and acoustic distribution of bubbles. Yeah. So these are all number of different techniques. Simple one for as far as processing is concerned, these are sufficient enough. Yeah. Any questions so far? Yeah. Yes. Your name is Kavya.
So my doubt is on multi-frequency bath with probe type, sir. Whether the product is led to process simultaneously or in batch types.
No, both together.
Both together.
Yeah.
Whether it will be effective, sir.
It was effective. That's why it was done.
So, because I have came across some literatures like the cavitation created by one piezoelectric transducer affects the other piezoelectric transducer.
Completely agree with you, because if you are having two transducer together,
yes, sir.
They both will be destroyed. Yeah?
Yeah.
So when these type of things are used, you have to use it. Suppose you have two probes. Yeah.
Yes,
it has to be like what you saw, the flat probe which was kept 400 frequency. They cannot be kept like this. They have to be kept like this. Okay. Yeah. So that is the important aspect of it. You read it correctly.
Okay.
Because if you put both, sound pressure comes from here, sound pressure comes from here, two different frequencies, it will destroy the transducer. So it has to be in a perfect alignment with that. So here it was done basically the length of was different, and then to combine both the frequency, and in that particular bath system you can have a transducer from the side, not from the bottom. Yeah.
Okay.
So that's why transducer configuration becomes an important part of it. Yeah. Same thing when we did for microwave extraction, You can use the water for extraction perfectly fine. The moment you put hexane and ethanol, it creates a vapor and any spark can cause fire. Yeah. So, usage also depends upon what is the solvent. So, you need to know the dielectric property of a liquid when we use it. Same thing for pulse electric field. If there are particles, it will cause a spark, or you cannot have air bubbles in a pulse electric field. Yeah. I cannot cover all the technologies, but these are some of the limitations for each and every technology. So, it has to be used based on understanding their proper working, yeah, and proper mechanism. Then only we should think of applying. Yeah. Now, microbial inactivation. Now, this is the viable cell. When you give ultrasound treatment, it causes pores on the surface. Yeah. This cell is not dead. Yeah. It causes pores and it can improve its performance so that substrate can go into the cell faster and reactant can come out faster. It only damages when pore size is slightly bigger, so that all the cytoplasmic material comes out of it. Yeah. So, there are studies where you do a calibrated pores because of ultrasonics, so that you can transmit DNA, cDNA or specific drugs into the system. As you can see from here, this is much clearer. This is favorite bacteria of dairy technologists, Lactobacillus sakei. Yeah. This is the normal cell. Yeah. You give ultrasound, you can see all the small pits. Yeah. This is at controlled energy delivered. Now, this is also a pores. Yeah. And then you extend the energy, then you get leakage of cellular content. Yeah. It's something like aqua or acupuncture. Yeah. You make a holes in it, so the substrate can go faster into it and end product can come out of the cell. Yeah. So, reaction will be faster. So, ultrasonic can also be used, especially a bath system can be used for improving the fermentation rates. Second reason is, when you add a microbial culture, you mix it. Yeah. But if you add a microbial culture, you give an ultrasonic, low power ultrasonic within that zone, it will distribute the cells widely. So, it can improve the performance. Same thing happens for microalgal cells. If you want to increase the growth, you can give ultrasonic control power, so that you have a better growth into the suspension. These are all open ended question. You investigate it, we will read it. Yeah. So, that is pretty much open area. Yeah. Now, this is TEM. We carried out the work on yeast to see how yeast can cause the pore, why yeast fermentation is improved. And when TEM was done, what was found, both the bacteria were working very well, but vacuoles disappeared. You know, every cell they have vacuoles, vacuoles disappeared. Then there was another question the person who was doing, what is the role of vacuoles in the cell? We will stop it there. Otherwise, we go into the fundamental to mechanism to other aspect. Yeah. So, that is the way the question starts with the simple problem and you get more and more complicated. That is why you create more scientific knowledge. Yeah. Otherwise, it is a cook and look. Then, in order to do that, we also wanted to see, is there any genetic modification happening in a cell, or why it is utilizing better nutrients. So, there again I am just stopping it there, because otherwise I will enter into utilization of nutrient, how it is modifying the system. Remember, only two different mechanisms, one causing the pores onto the surface, so that it can have a better reaction, substrate transfer. Second one is dislodgement of that particle, even distribution, like what you saw in first slide when you had a small black powder added with ultrasonic probe. Yeah. If you increase the energy into it, it will kill the cells. Yeah. So, same thing like when you aquapuncture, that therapy, you put a hole, it improves some of the problems of the body, but if you make a big hole in a body, what will happen? Yeah. So, the same thing works here. Now, ultrasonics, the same mechanism what we have already covered, comparing with thermal. Yeah. So, sono thermosonication can inactivate these microorganisms or to inactivate spores, yeah, by using heat and ultrasound together. Airborne acoustics. Now, what is the application of airborne acoustics? Now, we are a bit digressing from your biocircularity. Since I mentioned about the technology, it is important to conclude it for what it can be used. Non-contact microbial inactivation or process intensification. Take this example, yeah. How many of you have boiled milk? It comes up, right? What do you do? Yeah, same thing ultrasound does, because if you have big vat, you can't do it, yeah. So, this sound pressure goes on, it suppresses the foam, so that you do not have to add anti-foaming agent. When you are extracting the protein, it will create foam and it loses the product. So, you can use it as anti-foaming agent, yeah. This transducer, there are a couple of patents are there for design of those transducers, and these are industrial scale. Now, if you see this example, we all drink cola beverages, yeah, and this cola, not all, I do not drink much anyway. So, when you fill a carbonated beverages into a bottle, product loss happens because of bubbles. So, when it is filling in, airborne acoustic is kicked in, suppresses the foam, yeah. If in a day you have 2% losses, it is a huge cost. So, defoaming application, yeah. So, our purpose was not to use defoaming, our purpose was mainly to use it for inactivation purposes and to use airborne acoustic along with the drying system. So, this is a radiating plate and its focus point is 10 centimeter square, yeah, at a specific area. So, this was not a small system, is a big system. As you can see, distance is 405 millimeter, that is nearly 40 centimeter, and this is the distribution of acoustic power within this particular chamber. So, maximum intensity in the center and how it is reduced along with it. So, this can be measured by using hydrophone, by using normal sensor for measuring the sound intensity. Purpose: diagnostic probe, plasma jet filling in the plasma species and causing microbial inactivation, yeah. Now, when it was used, remember I was talking about high value spices and condiments, we do not use high temperature, just because if you use high temperature, they will not have those flavors. So, they have to be dried at low temperature. So, when we use airborne acoustic, it also helps in drying and also reduction in microbial load, but the timeline what you see is quite significant, yeah, 60 or 90 minutes. So, if this is combined, whether it is a black pepper or tapioca starch or any starch coming from any biomass or a protein, for drying, when we use this, we get significant reduction to a certain level, that is 1 log or so, and then if we combine with the plasma, this time can be reduced A. If we use it at 40-degree temperature, it will dry off faster, yeah. That is why when we are going through the seaweed, you would have seen ultrasound plus airborne acoustics, yeah. Now, we are covering about the technology, yeah. So, this is again percentage degradation of phenolic compound when was done with the black pepper, no changes, yeah, because it is airborne. Starch, no changes in rapid visco analysis, that is rheological properties were not changed and we do not want it to get it changed, yeah. So, these are just demonstrating different application. Some of the material is already there in print media. If you are interested in any specific thing, I will be happy enough to send it to you. Now, where this particular airborne acoustic and plasma system was used. Now, suppose this is the surface for biofilm, stainless steel, plasma water alone, thermal plasma, activated water, that means 2 different type of plasma water, and airborne acoustics, that is the same system. Control and ultrasonic was able to dislodge not that much. Water, plasma, thermal plasma, like different mechanism, different gas chemistry, when they both are attached with ultrasonics, complete removal of biofilm, yeah. So, airborne acoustic opening up the structure and plasma species causing inactivation. It is very similar, there are 2 people, one is breaking the door, other person is having a gun. You might have played lot of video games like that, yeah, it is a similar thing. So, then it's synergistic method. Yeah. Okay. So, that is the way it operates. So, this will just simple how we can improve the efficacy of specific system. Same thing if you do not want to use a plasma activated water, even if you are using a chlorine, you can reduce the usage of chlorine by employing new technologies along with it. Yeah. So, this is only your confocal microscopy to show how the things are changed only with control and ultrasound, dislodgement and then inactivation. So, we are not going to go deeper into it, just when we talk about technology, it's my duty to show where it's been used. Yeah. Now, coming back to your ultrasonic bath system, meat curing, fish curing, any of those one, brined fish. What is the purpose of brined meat or brined fish or brined pickle? Biomass added into salt solution, right? Salt slowly goes into and moisture comes out, your osmotic dehydration. But the same osmotic dehydration is carried out in ultrasonic system, you have a better result. It will speed up the process. So, one normal method is okay, it's becoming. One is normal dry salt. That means you have a product, you throw a salt on it, something like when a snail is walking around in a garden, you put a small amount of salt, it dies. Yeah, that is basically it draws out its moisture. That's why salt can kill, to take the moisture out. Yeah. So, in a meat you rub a salt on it, and after rubbing a salt, if you vacuum pack it, put it into ultrasonic bath, salt will diffuse uniformly. Yeah. Other one is immersion. You have brine, you put fish, you put meat, you put pickle, like what we do pickling. Yeah. And then other one is brine injection. That means you have a tough matrix, you inject a brine into it and leave it, you get salt migrated into it. The main purpose of brining process is the salt enters into the matrix. Now, how this system was designed? One, when the brining is carried out at commercial level, all those things are kept at 4 degrees Celsius, so that microbial growth does not happen, and other thing. So, in this case, this is the brine with the pump. The brine was passed through the heat exchanger to have 4 degree. Rather than having a big tank, maintaining the 4 degree temperature in a tank, we can have a normal tank, circulate the brine through the heat exchanger and to have a chilled effect. Yeah. Correct in saying that you have individual air condition in the room or you have a centralized AC. So, which one will be more efficient? Centralized air conditioning system. Yeah. So, similar way, instead of having multiple tank, each tank is maintained for 4 degrees Celsius. Lot of heat losses are there because you have to have a metallic steel tank. Instead, normal tank and brine is circulated through heat exchanger. Yeah. And then brining. So, example over here, piece of a meat going into the system and brining time, that is ultrasound and normal sodium chloride content of the product. Yeah. And then how it happens, this is the interesting part, not all this one. This is the surface of a meat. Yeah. When we give ultrasonic treatment, if you get a proper SEM images, you will see surface becomes like this, porous. Yeah. These are not like a big pore, these are at micropores because of ultrasound. That is why we call it sonoporation, and these red dots are sodium chloride measured by using a SEM EDX. So, when we do the salting, salt only goes between the fibers of a food product, as you can see over here. This is muscle fibers and salt is in between these. Yeah. Whereas, when we do sonication treatment, there is a uniform distribution of salt. So, whether you are using a brining purposes or you are using as a solvent for extraction purposes, mechanism remains pretty much similar. Now, any questions so far? No? So, some more valorization example we will cover when we go through tomorrow for biopolymer or feed application. Now, I added this slide. Yeah. Majority of us, not only you, including us, we are at this zone. Yeah. Cook and look into it. Yes, I can grow microalgae in a wastewater, done. Paper published, end of story. Yeah. whereas there are only few technologies which are commercial. A lot of you were asking question, what will be the cost of this, what will be it, yeah. But technology transition, yeah. Majority of the equipment which comes in a market, you don't, suppose you buy a domestic microwave, you don't change the frequency, you only operate based on whatever frequency is. So equipments are set to operate on a specific conditions, yeah. Fan, you don't change AC, DC, pulse duration and all those things, right. So once we know where we have to integrate it, so technology research and development, demonstration, system development and mission operation and integration. So lot of those type of systems, even in NIT Rourkela, you can see how those systems are designed, like automatic pickling machine, automatic dosa maker. What is the new technology there? Yeah, you've seen that. Automatic chapati maker, an automatic fryer for vada. You put a batter, it creates creates your vada and it moves to the oil and it turns and then you get the product, right. That is all technology development. You demonstrate it and then you integrate into the commercial line. It is not as easy as what is seen. So this is what I meant by technology readiness level. Basic principles observed, yeah. Then you prove the feasibility and then you develop accordingly. Like this morning, what's your name again, sorry? Kamaveshwari. So this morning she mentioned about when she used osmotic dehydration, lipid analysis was, lipid oxidation was less, yeah. So that is what basically what you have observed, yeah. Now you try to develop that, try to process in that line, that itself becomes a technology. It's not that, oh, it's just normal osmotic dehydration. No, it's not. Canning was discovered by Louis Pasteur way like almost 100 years ago, or yeah, nearly about 100 years ago. But still canning process is upgraded every time, yeah. So that's the way technology develops. Technology does not mean all those fancy probes, supercritical fluid extraction added here and there, yeah. But developed based on the need. You observe it and then you move forward. Same way piezoelectric transducer, piezoelectric properties of biological material was observed quite lately, and then that particular material now to run into make a biomaterial to replace quartz or to replace batteries. We don't have enough of metals to make a battery. So same thing as a solar plant, yeah. Solar system was not new, now you have EV cars, electrical cars. So that means it's been running. So that slowly development happens. But before things operate, you have to be in this zone. Majority of the food processing operation comes into this circle, yeah. So a bit how it works and bit what will be the commercial uptake of the process. Having those two things in mind is important while doing any processes, yeah. But remember, you cannot answer everything in one single experiment, yeah. So any questions so far? No? Actually this particular slide was for market uptake, value chain and how we integrate it, yeah. But remember, I will come back to this one again, right. So that is why it is important to know what we do, yeah. It is good to have those questions, yeah. I do get often these questions, whether this technology can be used in industry or what will be the cost of the technology. I have simple answer, take my phone out and this one. 1990, nobody was having phones, yeah. Like you all have iPhones. When we were studying, we had no phones, yeah. But now systems are there. Slowly systems are upgraded. So, but who should get the Nobel Prize for phone? Who is the first inventor? Graham Bell, yeah. Developed that phone, and everything is developed based on that, yeah. Same way your osmotic dehydration was done from centuries, yeah. But now you see where it can be used, yeah. So then you slowly nurture that one. You don't ignore. That's why observation becomes very important in any of the unit operations what you do, yeah.